So good morning, everyone. My name is Anna Wolny. I'm PhD student from Silesian University of Technology. And today I would like to present you my research on active and stable biocatalyst for the continuous flow synthesis of C8-C18 carboxylic acids esters of biomass-derived furfuryl alcohol. This work was founded by National Science Center in Preludium grant, which I lead. So firstly, I will highlight the main goal of my work. Then I will speak about the importance of support designing for efficient immobilization and how I synthesize my biocatalyst. Then I will skip to the results of activity test of designed biocatalyst in model reaction, which was furfuryl esters synthesis. Then I will go from batch to continuous flow synthesis of furfuryl esters, and in the end, conclusions. So the main goal of my work was to develop more environmental friendly technology of synthesis furfuryl esters. And it was done by following with sustainable development goals, especially goal number 9, what is industry and innovation, goal number 12, responsible consumption and production, and goal number 13, climate action. And for me, and what is directly related to my work, in developing a green solution for sustainable production can be achieved by implementation of enzymatic technologies, the use of substrates from wastes, and the flow synthesis development and its potential implementation to industry. The proper support designing in maintaining enzyme activity as well as its efficient immobilization is crucial factor in synthesis high active biocatalyst. And what is well known in case of lipases activations occurs in hydrophobic environment, what is called interfacial activation. And in these conditions, the lid which covers active sites is opening and enables free interaction with active sites with substrate, as well as its efficient immobilization. So it's very important to rethink which support to use to obtain high stable and high active biocatalyst. And sometimes, for some reasons, we don't want to choose hydrophobic supports as for lipase immobilization, as for example carbon materials like carbon nanotubes or activated carbon. So for some reasons, like for example price or some structural properties, we want to choose some other kind of support like hydrophilic silica. And in that case, some physical or chemical modification of the matrix should be required to maintain and to enable efficient immobilization of the lipase on the surface. And what is worth to mention here, the immobilization not only enables high active performance of lipase and maintain its stability, but also enables efficient separation of the catalyst from reaction mixture and also its recycling in the process. So taking into consideration all of these aspects, which I said, I chose as my support for lipase immobilization hydrophilic hybrid material consisting of magnesium oxide and silica, and I will explain myself now. I chose that material not accidentally because it's well known that the presence of magnesium groups in the material increased the affinity of enzyme towards the matrix, so increased the efficiency of immobilization due to the increased porosity of the material. And also the presence of magnesium particles in the structure maintain high active performance of the lipase, and also stabilize the active conformation of the enzyme during the process. And to make my support more suitable for efficient immobilization of the lipase, I performed modification of the surface by chemical immobilization of alkyl groups with 8 to 16 carbon atoms. So it was octyl or hexadecyl groups. And then after that modification, I performed lipase adsorption on the surface, and it was lipase from Aspergillus oryzae. I chose that lipase because that lipase indicated the highest activity in studied process, which was esterification of furfuryl alcohol with carboxylic acids. So here I wanted to show you various combinations of biocatalysts I made. And that biocatalyst was characterized in means of the amount of alkyl groups as well as the amount of immobilized lipase. And I calculated these amounts, I mean alkyl groups and the amount of the lipase, based on thermogravimetric analysis. And as you can see, the modification of magnesium oxide silica hybrid material with octyl group enables immobilization of the lipase on the matrix, because as you can see, without without modification, the lipase was not detected on the surface of the materials. And the longer alkyl chain resulted in decreased amount of immobilized alkyl group, as well as decreased immobilized amount of immobilized enzyme, probably due to some steric hydrants because of the longer alkyl chain. And I also tried to calcinate firstly my support before modification with alkyl groups to make some changes in structural properties, but it also did not affect to better immobilization of alkyl groups or enzyme, probably due to reduction in hydroxyl groups availability on the surface. And as you can see, the introduction of magnesium oxide to the silica resulted in increased alkyl groups on the surface, probably due to higher availability of hydroxyl group on the surface in this example, but less enzyme was immobilized there. So I will make some spoiler right now, because the highest catalytic activity showed the biocatalyst consisting of magnesium oxide and silica material modified with octyl groups with adsorbed lipase from Aspergillus oryzae. And for that biocatalyst, I determined the specific surface area, pore volume, and pore diameters. And as predicted, after introduction the alkyl groups and after enzyme mobilization, the specific surface area decreased. I also performed images in scanning electron microscopy, and as I showed here, as you can see, the particles agglomeration increased after introducing the alkyl groups and after enzyme immobilization. So I tested all designed biocatalysts in esterification of furfuryl alcohol with octanoic acid to produce furfuryl octanoate. Here in this reaction, which was according to the literature, made in the present some acidic catalyst. We've used metal-based catalyst or heteropolyacid-based catalyst. Here, the selectivity is very important. In that case, in these cases, the selectivity was very low due to the fact that furfuryl alcohol can very easily create ethers or thermostatic polymers. So in my enzymatic approach, it was very important to achieve high selectivity. And as I said before, it's very important to use the substrate which can be somehow obtained from waste. And furfuryl alcohol is a biomass-derived compound. So this is very sustainable approach for the process. Also, furfuryl esters are applicable as biofuel additives, flavors, fragrances, surfactants, bio-based polymers as plasticizers or emulsifiers. I optimized parameters for my model reaction for furfuryl alcohol actinoic acid esterification in range of the choice of proper biocatalyst amount, which was 150 milligrams per 1 millimole of furfuryl alcohol, temperature, where room temperature was enough to maintain high technological parameters. As solvent, I chose cyclohexane in amount 0.5 milliliter, and alcohol to acid molar ratio was 1 to 3 furfuryl alcohol to octanoic acid. And for chosen biocatalyst, I also tested it towards other carboxylic acids, which are considered as fatty acids, so from 8 to 18 carbon atoms in alkyl chain. And finally, the results from catalytic activity of designed biocatalysts. What I want to add here, that I calculated all the catalyst amounts to put the exact same amount of lipase to the process to make my results comparable and to show the influence of the support to lipase performance. So, and as you can see, for all examples where the matrix was modified with alkyl groups, the activity of the catalyst was improved, and as you can see before, the introduction of alkyl groups enabled efficient immobilization of lipase. What is also very visible here, the introduction of magnesium particles on the materials, not here, resulted in higher catalytic activity of the lipase. So here, the influence of introduction of the magnesium particles is very visible. And the longer alkyl chain did not increase and it did not decrease the catalytic activity of the lipase, as well as the previous calcination of the support, but they affected to the immobilization of enzyme on the matrix. So as the most suitable for studied process, I chose the biocatalyst consisting of magnesium oxide and silica modified with octyl groups with adsorbed lipase from Aspergillus oryzae. And for that biocatalyst, I also made the stability tests. So the biocatalyst stayed stable through 9 reaction cycle, and in 10th reaction cycle, we can see slightly drop in activity and slightly drop of conversion from 90 to 85%. And as I said, I tested my biocatalyst towards other carboxylic acids, which are considered as fatty acids, and that biocatalyst enabled me to produce all of these esters with very high conversions and quite high isolated yield of esters. And encouraged by this very nice results from stability tests, I decided to transfer my technology of furfuryl ester synthesis to continuous flow synthesis. I made my experiments in a column microreactor filled with 300 milligrams of chosen biocatalyst. I made optimization parameters in range of the flow, and the best was 0.07 milliliter per minute total reagent flow at room temperature, with the residence time of the reagents on the catalyst 10.5 minutes. I also calculated space-time yield, which was 458 grams per hour milliliter and milligrams of immobilized lipase. And under these conditions, the conversion reached 97%, which 100% of selectivity. So the process transformation enabled from me in that case a more efficient production of esters. I also made for the continuous flow system stability test of my designed biocatalyst, and as you can see, the biocatalyst stayed stable through 40 hours of the process, and after that time, slightly drop in activity to 89–88% was observed. So to conclude, the designed biocatalyst consisting of magnesium oxide, silica modified with octyl group, and adsorbed lipase from Aspergillus oryzae was developed, characterized, and it exhibited very high activity and stability in the esterification of furfuryl alcohol and C8-C18 fatty acids. The biocatalyst enabled synthesis of furfuryl ester in both batch and continuous flow systems. The yields of furfuryl ester synthesis for batch 88% and for continuous flow 97% with selectivity 100% were very high. And the developed process is more environmentally friendly, aligned with the principles of green chemistry and sustainable development goals, which was the main goal of my work. Thank you for the attention and for letting me to present here.
Thank you very much.